Higher education faces growing class sizes, limited instructional capacity, and uneven student outcomes. Institutions must scale quality teaching without exponentially increasing costs. Student diversity requires personalized pathways to keep learners engaged and progressing. Traditional systems struggle to predict who will disengage before it's too late. This video explores top-rated EdTech tools that solve these challenges at scale. We focus on 3 benefits: scalability, AI-driven personalization, and predictive analytics. Scalable platforms support thousands of learners through cloud-native infrastructure and automation. They reduce operational overhead while maintaining consistent course quality and access. Automated grading, content distribution, and integrated tools streamline faculty workload. Scalability enables institutions to expand programs rapidly and reach more students. Cost per student decreases as systems leverage shared resources and intelligent orchestration. Scalable EdTech forms the foundation for personalized and data-driven learning at scale. AI analyzes learner data to create individualized pathways aligned with goals and gaps. Adaptive assessments adjust difficulty in real time to keep students in their optimal zone. Personalized content recommendations guide learners through the most effective sequence of materials. AI tutors offer targeted feedback and scaffolded practice tailored to each student. Faculty maintain curriculum oversight, while AI handles routine differentiation and pacing. Such personalization increases engagement, mastery, and timely progression through programs. Predictive analytics use patterns to identify at-risk students early and reliably. Data signals include performance trends, engagement metrics, and assessment behaviors. Early alerts enable timely interventions, like coaching, tutoring, or curriculum adjustments. Studies show predictive interventions can materially improve retention and completion rates. Clear data visualizations make insights accessible to advisors, faculty, and administrators. Transparent dashboards support evidence-based decisions and continuous program improvement. Successful adoption begins with pilot programs, stakeholder alignment, and measurable goals. Integrations with SysIS, LMS, and assessment systems ensure seamless data flow. Training and change management empower faculty to use AI tools effectively. Monitor KPIs such as retention, time to degree, and learning gain improvements. Real-world deployments demonstrate scalable impact on access, equity, and academic success. Start small, measure outcomes, scale proven solutions to transform higher education. Imagine stepping inside a lesson where concepts become places you can walk through and explore. This is virtual reality learning, fully immersive, sensory, and designed to reshape how students remember. Over 3 minutes, we explore VR's effects on spatial memory, emotional intelligence, and empathy in learners. First, spatial memory. VR turns information into immersive places students can navigate and recall. Researchers find that learning locations and routes in VR forms stronger mental maps than text alone. That immersive context anchors facts to spatial cues, improving recall when students mentally revisit the scene. Controlled studies compare VR navigation tasks to textbook study for geography and anatomy lessons. Students who trained in VR often show faster route recall and better landmark recognition over weeks. Neuroimaging and behavioral tests suggest VR engages spatial networks more naturally than abstract repetition. Key point: embodied navigation links memory to movement, supporting deeper encoding and longer retention. Now, emotional intelligence. VR can simulate complex social cues for safe practice and feedback. Role-play scenarios in VR let students rehearse emotional responses and receive objective performance data. Multiple studies report improved recognition of facial cues and regulated responses after VR practice sessions. Simulated conversations with branching responses expose learners to nuanced emotions without real-world risk. Empathy studies use perspective-taking VR, placing students in another person's lived experience. These simulations reduce implicit bias in measured scenarios and increase willingness to help in follow-up tasks. Critically, fidelity matters. Higher realism often yields stronger psychological effects, but design must target learning goals. Across domains, VR's active, embodied practice offers measurable gains beyond passive instruction alone. Compare side by side VR simulation versus traditional lecture and textbook study for the same lesson. Data overlays show higher engagement, faster skill acquisition, and improved retention in many VR conditions. But VR is not a replacement for all methods. It complements hands-on practice and reflective discussion. Researchers emphasize integration, scaffold VR experiences with prompts, guidance, and post-experience reflection. Ethical and accessibility considerations also shape outcomes. Design must include diverse perspectives and accommodations. With that evidence in mind, what practical steps should educators take next? Start by defining clear learning goals that VR uniquely supports, such as spatial reasoning or perspective taking. Choose simulations that align with assessment methods and allow measurable practice and feedback. Scaffold experiences with pre-briefs and VR prompts and structured debriefs to deepen learning transfer. Train educators on facilitation and interpretation of VR analytics to make informed instructional choices. Prioritize accessibility, offer alternative formats, adjustable settings, and clear safety protocols for students. Start small with pilot programs, gather data, iterate, and scale what demonstrably improves learning outcomes. By 2050, screens and keyboards still dominate learning, but their limits are increasingly clear. Attention, context switching, and physical accessibility slow down knowledge transfer for many learners. Visual screens require focus, hands, and space, barriers that persist across ages and abilities. Bandwidth for meaning is limited by tight text, video latency, and interface friction. Teachers and designers work around with scaffolds, but fundamental transfer remains indirect and slow. This sets the stage for a radical alternative: direct neural interfaces, delivering semantic data. Non-invasive BCIs read and write patterns of neural activity without surgery or implants. By 2050, these systems will map high-level semantic representations, not raw sensations or spikes. Imagine concepts, language, and structured knowledge transmitted directly to cognitive networks. Sensors, advanced algorithms, and adaptive interfaces translate between neural codes and educational content. Crucially, transmission focuses on meaning, semantic payloads optimized for understanding and retention. All of this happens without invasive procedures, enabling widespread, flexible adoption. Compare current workflow: eyes to screen, hands to keyboard, slow symbolic translation. Now compare BCI workflow: intent and concept flow directly, bypassing intermediate devices. Data rate for semantics increases dramatically, while latency and friction approach negligible levels. A simple diagram shows screen pipelines versus direct neural channels and their performance differences. Keyboards and hands become optional. Multimodal inputs and natural language integrate seamlessly. Visuals emphasize cool blue UI overlays and clean minimalist diagrams to clarify contrasts. Learning becomes personalized at neural timescales, adaptive to attention and memory states. Students can receive semantic scaffolds directly, compressing explanations into precise cognitive cues. Accessibility expands. motor impairments, visual limitations, and language barriers are significantly reduced. But privacy and consent become central. Thoughts and semantic states must remain protected by design. Policy, encryption, and decentralized control models will be essential to safeguard learners' minds. Ethical frameworks must balance empowerment with autonomy, avoiding coercive or surveillance-driven education. By 2050's end, adoption may be widespread in schools, training, and lifelong learning platforms. Designers should prioritize legibility of meaning, consent-first UX, and inclusive content strategies. Educators must evolve assessment, focusing on comprehension, reasoning, and ethical reasoning, rather than rote recall. Technologists must build transparent models, verifiable semantic codecs, and robust privacy guardrails. Communities, policymakers, and learners should co-create standards and equitable access programs. The future promises faster, fairer learning if technology serves human flourishing, dignity, and choice. Every year, many students leave university before graduation, hurting careers and institutional performance. Dropouts often stem from issues that appear early: attendance, grades, finances, and engagement. Traditionally, universities react after problems escalate, making support costly and less effective. What if universities could spot risks months earlier, then act proactively to keep students on track? Predictive analytics makes that early detection possible by analyzing large, diverse student datasets. This video explains how predictive models find at-risk students and enable targeted, timely support. Predictive analytics uses historical and real-time data to estimate each student's risk of dropping out. Sources include grades, attendance, learning management activity, advising notes, and financial aid records. Machine learning models detect patterns humans might miss, combining signals into a simple risk score. Dashboards translate complex outputs into actionable insights for advisors and student success teams. Models are continuously recalibrated with new data to keep predictions accurate over time. The result: early, reliable identification of students who need support before crises develop. Risk factors are weighted: falling grades, missed classes, low engagement, and financial stress. Individual risk scores are updated weekly so advisors see the most current picture of student well-being. Visual flags on dashboards highlight students with rising risk so teams can prioritize outreach. Alerts include the primary drivers behind each risk score, enabling targeted intervention planning. Predictive insights can identify issues months before a student considers leaving school. That early window creates the opportunity for effective, low-cost interventions with higher impact. Once identified, students receive tailored interventions such as tutoring, advising, or financial counseling. Interventions are prioritized by urgency and evidence of what works for similar students. Automated outreach can schedule appointments, send reminders, and deliver targeted resources instantly. Advisors use model explanations to personalize conversations rather than guessing causes blindly. Coordinated workflows connect tutoring, counseling, financial aid, and faculty for holistic support. Small, timely actions often prevent escalation and keep students progressing toward graduation. Universities using predictive analytics report measurable gains, higher retention, and improved graduation rates. For example, pilot programs commonly show single-digit to low double-digit percentage increases in graduation. Beyond numbers, students experience improved advising, timely help, and greater confidence to finish degrees. Implementing predictive analytics requires careful data governance, privacy safeguards, and continuous evaluation. Start small with a pilot, measure outcomes, expand what works, and keep students at the center. To learn how your university can get started, contact the Student Success Office today for a consultation.